So today we began sort of the last little bit. This is a segue really into 1080. A lot of what you all will do in 1080 will be basically intervals, which is what we're going to start right now. And what is this business with intervals? Well, you spent all of 1040 and I guess most of this class doing derivative type stuff, right? I mean, derivative this. We started with implicit differentiation. You finished in 1040 with the chain rule. Then we did a lot of applications, derivative, linearization, all the stuff derivative everywhere. There's really no difference between the math you did before and calculus now, except for one thing, and that's the notion of a limit. And the derivative was a certain limit, right? You start off with those secant lines, kind of sort of tangent line. And at first, it's just like you're contemplating your own navel, but then it turns out that this way to change things shows up everywhere. There's another classical problem in calculus. The one that we've just tackled, and this sort of sells it short, but the classical problem in calculus we tackled is if I have this point here on this function, what's the slope of that tangent? And of course, the slope of the tangent line measures the instantaneous rate of change. Rates of change are everything, physics, science, and things like this, engineering. And so we have a lot of stuff just coming from this notion of the limit here. The other classical problem in calculus is this. Suppose I have some function. And the classical problem in calculus is what is the area of this? How do we define it? What is it? What is it? And you know what? I got 3 out of 4. Straight side, straight side, straight side. I can do anything straight side, right? I can do triangles, I can do rectangles, right? And so I can do any polygon. The polygons can be made up of triangles, right? What's killing me here is it's got a curved top, right? That I don't know. Right? What's the area of this curve? The root's curved. So there is one curvy thing that you do know how to do though. Anybody know a curvy geometric object where you know what the area is? Circle. Right? Here's one thing you know. I can have a lot of explain what it is. If you have a circle, a radius r, the area of this, but you know what? Here's something I can find. How old were you when you learned that formula or encountered it? I mean, you probably knew it before you formally encountered it, right? You saw it, right? I mean, because this is like in popular, culture, right? You'll see there certain objects. Maybe you're in grade school sometime when you were first told this hardcore, right? So it's at the area of certain power square, right? Let me tell you why. I mean, that's like being in church, isn't it? Right? There's a little place required. Power squared. It sounds good, but nobody ever showed it to you, right? Well, that's true. Well, there's anybody know where they first came up with this? Or what would it do? Way to do this. Okay, I'll tell you what I'm gonna do. I'm gonna approximate a circle. A circle is like a triangle, right? That's an approximation. Measure the area of that triangle. Okay. That's going to stink, right? Because the triangle, look, is much smaller than the circle. If I agree with it. But I could, if I'm thinking like an engineer, I might put a triangle around the circle and average the two. Right? That might be it's quite not exact. And the key is I can do a triangle, just get straight sides. Yeah, the triangle doesn't look like a very good approximation. What's a better approximation? Well, better the square. Because it looks like you lose out on less. You might even do better. Pentagon. Or if you're really full of energy, do, I don't know, 256 down, but you can put a gon with like 200 sides on it, right? And these sides are just little slivers, right? That's going to approximate the circle pretty good. Certainly better than the triangle. Would everybody kind of intuitively agree that if I put a regular n-gon with a million sides in here, I'm going to probably with my eyeballs almost be unable to distinguish that. So, right. This is again a calculus idea, because as the number of sides of my gon get bigger and bigger, I should get closer and closer to the area of the circle. This is a limiting process. And really, that's the only thing that's different from all the algebra and trigonometry we had earlier. Calculus, all that stuff, one more notion, a limit. Used here to find a tangent line, and we're going to use it here to find areas under the curve. And again, you can see that that has lots of applications. This innocent looking area under a curve, which might be considered as sort of somebody's boring abstract kind of question, actually shows up all of them. Okay, so that's kind of a, oh, here's another. This might come in a little later. Suppose I had a semicircle, right? The total area here is 1/2 right? And by the total area, I mean just the area of the semicircle under the top dome and above the x-axis. Everybody move the x. What if I just wanted this piece? Out to say here, something like t, and so function here, governing function is y, square root of r squared minus x squared. This just means it's the upper half of the circle. Right? Here's something curvy. It's a piece of the circle. You better figure out what that is. Let me take it. Let me think of this. Everybody's comfortable with this. Does anybody know what a sector of the circle, what its area is? So let's suppose that I have a piece of slice that I've taken out of the circle, and it's got area angle theta, and we'll say it's got radius on. Do I know what this is? Yeah, because it's got that curvy in it. You're close. Actually, you're on the track here. Area of the sector. I bet it depends on r squared. There's an r squared. Do you know how to know that? Units. Right? R is measured, say, in inches, right? The area that piece is in square inches. I bet it's like this. By the way, let me ask you this. When theta is 2 pi, what does my piece of look like? If theta is 2 pi, what does my slice of pizza look like? It's the whole pi. Everybody agree with that? And I know where it should be if it's the whole pi. So the area should be proportional to the square of the radius, and it should somehow depend on how big that angle is. That's not quite either. But if I put in theta is 2 pi, right? If I had the whole slice, then that gives me a formula for the area of the circle 2 pi r squared. There you go. How many of you have seen this? Maybe you didn't remember it, but you can count some. Right, you take the angle measure, we have a circular sector, square the radius, times the angle measure times 1/2. And the way I always to this day remember this formula is this. What should happen when theta is 2 pi? It's the whole slice of theta, pizza should be good. So. Everybody okay? So. Can somebody look at this kind of thing I've got in red here and tell me, now that I know the formula for this, how can I figure out this? Very good. Most excellent. It only make your triangle better than that. There we go. So if I do that, I have a triangle of these that I can figure out because I know the x coordinate is t and the y coordinate is whatever you plug in this formula, right? And then I have this angle here, theta. Ooh, that's my problem. How do I measure that? Well, I'll give you another cue. This length right here is t. And then what's the length of this hypotenuse? It's pretty simple. There you go. This angle here should be the same as this angle. Right? Anybody agree with that? Because these are like two parallel lines here cut by transversal, so these make it the same. And now I know what this, I can use trig to find this, right? Because the sine of this angle should be this over this. So I can get the triangle from x coordinate and y coordinate, and then add on the area of this, and the only missing piece is what theta is, but I can figure that out using trig, right? It's an inverse sine. But every example that I've done depends on the circle. Yes.
So I understand how you find the bottom triangle, but how do you find like the other side?
You mean the piece? Well, this piece is 1/2 r squared theta. So you're almost done. You just don't know what this is. But this triangle here, this theta and this theta are the same. This triangle here, if the sine of theta is, well, somebody tell me what the sine of theta is. So theta is the inverse sine. And if you put that together with a triangle, you should get a formula. It's rather complicated. There's an inverse sine and there's a triangle. So some square reason, I guess. You can do it. But again, this depends on knowledge that I think I have from like, maybe 8th grade or something like that, when somebody told me what I wouldn't say it's maybe 12th grade, but anyway, at some point somebody told me what the area of the circle was. And I'm not even sure where that came. But if I have something like this, suppose I want to know what the area of the tip of that parabola is between the x-axis here, right? What I want to know this area. That's got a curvy top. That ain't a circle. That's nothing I've dealt with before. How do I figure this out? And that is a problem. That is a fundamental problem that we're going to attack. But before we attack this problem, I need to develop some notation a little bit. How many of you have ever seen sigma notation when you worded it third part? Well, sigma notation is this is a shorthand language. So for example. Suppose I wanted to add up the first n and 1 plus 2 plus 3, and n might be very big, it might be a million. Nobody wants to write all that crap down, it's cumbersome. Does anybody know how to write this shorthand? Well, if you're thinking of factorial, not multiply. This is the capital sigma in Greek, sigma for sum. Think of this as a little counter, right? This starts at 1 and it goes to n, counting up all the time. K equals 1 to n, and the sigma notation means add it up. Right? So when you start at k equals 1, you get 1. There it is. Plus sigma, then you're at k equals 2. There we go, add it up, and k equals 3. There we go, add it up, all the way up to n. Right? So this is a shorthand way of it. Right? But for example, remember example, I wrote this down. Let's do this. Let's do this. This just means there should be 5 terms that I'm adding up. The first term, k equals 1, 2. K equals 2 is 4 plus 2 is 6. K equals 3 is 9 plus 3 is 12. K equals 4 is 16, 4 is 20. And K equals 5 is 25 minus. Let's see how I do. You don't have to start with 1, you don't have to end with anything in particular. This just means counting off, right? I start at 3 and I end at 6. So this is the k is 3, I have sine of 3 pi over 4. And k equals 4, I get sine 4 pi over 4. K equals 5, sine 5 pi over 4. And k equals 6, I get sine 6 pi. And this is what it is, whatever number, let's see. 3 pi over 4, sine 5 is minus 1 over radical 2, sine pi is 0, sine 5 pi over 4 is minus 1 over radical 2 as well. Sine 3 pi over 4 is actually not bad. Sine 5 pi over 4 is minus 1 over radical 2. Sine 6 pi over 4, that's 3 pi over 2, is minus 1. So this adds up. Any questions?
Yeah, how to think they're
Just by plugging into the formula. So this is like a counter. This goes k equals 1, 2, 3, 4, all the way up to n, right? And you add up along the way. So when k equals 1, plug into the formula, I get 1. K equals 2, plug in the formula, I get 2. And then you add it up. So actually, maybe And that's the way I got it here. I got 1 squared plus 1, then k equals 2. I get 2 squared plus 2, k equals 3, 3 squared plus 3. And 4. That clear? Okay. Now, I'm gonna actually formulas that we will use. I don't require you to memorize these. They're kind of interesting. This one actually comes to a great story. Let's do this. This means that at first in case 1, case 2, 3, and then n minus 1, and then 5. Anybody know what this? Actually, there's a very famous story. How many of you have ever heard of Gauss? It's one of the most famous mathematicians of all time. You'll hear about this person when you get up in calculus, but there's a lot of laws, physics, and math. So anyway, the story was is he was a child in like grade school, whatever we call grade school back in the 1700s. And you know, it was like Little House on the Prairie where they're sitting around the slates, right, to write on. And the teacher, apparently wanting the class to leave him alone, asked the students, okay, add up the first 100 numbers, right? 1, 2, 3, add that up. This is going to keep your class out of your hair while you recover from your hangover, right? And so that's what the teacher did. And like the teacher sat down and put his class to work, and Gauss came up like after 8 seconds, had the answer. The teacher dismissed him, said, "Go sit down, you can't." Possibly added them up. And so he sat there with his head on his desk, and in the class, it turned out he had written down the right answer. Anybody know what the sum of the first 100 integers is? Should be 5,000. You must see how to do it. See, this is the thing. You learn the math rules. What you should learn after a while is to start to use the math, the level math. That's what Gauss had to figure out. He had to add up all those numbers. Agree? Nobody wants to do this. This is also static. Now add vertical. What's 1 and 3? What's 398? So if you add 1, by the way, how many times do you add this to Excel? One thing, let's see. Yeah, there should be 1 for every all. So there should be 100. So 100 times 101, which is pretty easy to figure out, should be twice his answer. So S is 50. 101, 5,000. But you're done and you take a nap. Right. The punchline is Gauss did this third. Right. Not too shabby. By the way, there's nothing special about the fact that I used the number 100. Right? In fact, let me change this artistically. In our own formula. Let's do the same thing that we did last. Add the columns. What's one and n? And plus one, right? What's two added to n minus one? And plus one, 10. 3 and n minus 2, and plus 1. All these add up to n plus. How many of these do we have? How many of these do we have? Well, see, there should be one for 1 plus n, 2 plus 3, 4. There should be enough. So n plus 1 added to itself n times the 2s, and I use more general formula. Notice when you plug in 100 for n, you get the 5,054, but now this works for you. Any questions? Anybody want to get some? I'm not doing this. What happens if you add up for n squared, right? I'm up in both. Yes. This is why. This n plus 1 is 2n plus 1, all divided by 6. You can test it out to a few to see if it works. I'm going to prove this works, but this formula will probably be used a little bit later, and I'll give it to you. By the way, I can do this for any positive power, but I don't after this. Kind of obnoxious. What happens if you add up first in cubes? Anybody see a pattern here? There's actually kind of a pattern. When I add up the first power, my formula is quadratic in n, right? Because there's an n squared. Right? When I add up the squares, when I have the second power, the formula is cubic. Because the highest term here is 2n cubed. When I add up the first cube powers, the third power, this is actually a fourth. But the specifics of this, we might use that a little bit later. Now, we can get some areas under the curve, right? So here's another motivating example. 2 miles per hour. And traffic 2 hours. How far have you gone? Okay, this is kind of a silly question, right? But and it's easy in a certain sense with regard to our picture, but I'm gonna kind of justify this here, or use this kind of hopefully increase our understanding. So if I travel for 2 miles an hour for T hours, how far do I go? 2 times T miles. Whatever it is. I can draw a picture of this. And follow this. Let's start at time. 0. What's my velocity? Always 2 miles an hour, never changes, right? So if I were to draw a graph of my velocity function, what would it look like? My v of t is always 2. So it would in fact be a horizontal line. Exactly. And I'm going to change this. So let's say that I travel 8 hours. I'm going to change this to 8. I don't want to be variable here. So if I travel with this velocity 2 miles an hour, and then I stop after 8 hours, I went 2 miles. Right? Agree with that? 2 times 8 is how far? What is the area of this box? The area of this box is the height times the width, which is 2a. Now, a can be anything. You 1, 2, 5, whatever. Notice that when I travel, or when I travel for 8 hours, the area of this box always tells me how far I've gone. This is actually my point. It's the area of this box tells us this. Keep these in mind. These are formulae that are in your book, but just know that they exist in case I need to pull it out. What if I travel for 8 hours, but my velocity is 2t, right, miles per hour. So in this case, I'm speeding up, right? So if I were to graph my velocity now, my velocity is variable. So this is like I'm accelerating a car. In fact, it's very much like I'm accelerating on gravity. I'm accelerating at constant rate. So when I start the clock, my car ain't moving, and I step on the gas. After, maybe I should put seconds in more present. After an entire hour, I'm going 2 miles an hour, right? So I'm kind of accelerating so slowly there, but nonetheless, I'm doing it, right? So after 1 hour, I'm going 2 miles an hour. After 2 hours, I'm going 4 miles an hour. After 6 hours, I'm going 12 miles an hour, right? How far do I travel? What does my velocity function look like now? Right, it's a straight line down, it's got a slope, it's got a slope too. Right? and this is D of T 2T. Now, how would you, okay, most of y'all are engineers. This is something, here's the problem. Distance, distance is your velocity times time, right? If it's constant. Here my velocity is not constant, it's always increasing. At every second, my velocity is increasing. Now I can't really use distance as velocity times time because it's always changing. So how can we ballpark this? Everybody agrees that velocity is a constant, right? But here's one thing that I can do, and this is kind of an engineering way to think about it. One thing that I could do is this. I could say, well, my velocity is always changing, but I'm going to measure my velocity at the halfway. So say A over 2, and then I'll measure the velocity here. And I'll use that, right? So I'm going to try to see, what I'm doing is I'm approximating this triangle, which should be how far I travel, the area under it by this box, right? So I measure, since my velocity is always changing, I measure my velocity right at the halfway point, A over 2, right? And I say, well, how far have I traveled? What's the area of this blue box? Well, is A over 2 is its width, and its height is A. So I traveled A squared from 2. Width is A over 2, height is A. And the width here is A over 2. What's the height of this box? Well, this point is point A, 2A. So the height of this box is 2A, and the width is A over 2, so I get A squared. So my estimate for how far I traveled is A squared over 2. Right, plus A squared. So I estimate 3 halves. By the way, do you think that estimate's too big or too little? If I travel 8 hours, my velocity is 2t miles per hour. Do you think that's an overestimate or an underestimate how far I travel? Well, we're estimating how far I've traveled in this bit first. Everybody agree with that? And the velocity that I measured was at the fastest point in that interval. Agreed? So I said, well, I'm going to pretend that I spent the last A over 2 hours doing my fastest speed. This is probably going to be, it's going to tell me I'm going farther, right? And I did the same thing here, right? I said I traveled another A over 2 and I measured it at the fastest point. Probably no overestimate. How can I make my estimate better? Let's break it up. So let's do this. Let's see how this changes things. And of course, you know, if you've got a computer, it'll go real fast. Let's do this. Let's break it up into a smaller chunk or A, 2A. Let's break this up into 4 pieces. This is A over 4, A over 2, 3A over 4, and A. So my height here is point A, 2A. this is point 3A over 4, 3A over 2. This is A over 2A, and this is A over 4, A over 2. So I drive A over 4 hours. I measure my speed there. My speed is A over 2, and the width of the box there are, and I travel that, so distance times time is going to be A squared over 8. So my estimate is I travel A squared over 8 in this first bit. Here, my width is still A over 4, but now my height is A, so my speed is A. I measure my speed. And I say I'm going to end up traveling A the entire length. That's A over 4, so I get A squared over 4, I guess. Here, my speed is now measured at 3A over 2, and again times A over 4, so I'm going to get 3A squared over 8. And finally, my measured speed here at the very end is 2A, it's A over 4, so I get A squared over 2A. So now my estimate 2. Let's see. What do I get? A squared over 8 plus A squared over 4 plus A squared, 3A squared over 8 plus A squared over 2. So this is, that's 4A's, so I get 1/2 A squared. And this is 3/4. Oh, I'm sorry, this is half. 4A's half, and this is 3/4. So I get 5/4. What can you say about the second estimate as opposed to the first estimate? Six-fourths A squared, 5/4 A squared. It's a little smaller. You think it's more accurate? It was more accurate. How can we make it better? I can do this 8 times, for example, right? Yeah. Let's do that. Let's do this a whole bunch of times, right? Any ideas on how to do this a whole bunch of times? Let's break this up into a very, very large number of little boxes, right? Large number, let's say n, evenly spaced boxes. And let's measure the area of each box. So I'm going to call this the cake box. Each box is, how wide is each box? If I break this up into n boxes that are evenly spaced, right? How wide is each rectangle? I'm trying to build a rectangle. How wide is it? Well, ask yourself this. How wide is the entire interval? This is what we're breaking it up into. How wide is that? A. Everybody agree with that? So I've got something of length A that I want to break up into n equal pieces. How wide is each piece? Each box should be A divided by n length. A is total length and n number of pieces. If you got 10 people eating a pie and you want to be fair, everybody gets a tenth of that, right? And that's exactly what we're doing here. We've got 80 units long and we want to break everything up into it. We want to be fair. I am also, just like this, I am going to use the right-hand endpoint to determine the height. Let me, so what is this point here? What's the first endpoint that we get? This is 0, right here at the origin. And how far is it from here to here? A over n. Right? It's the width of each. The next one is 2a over n. The next one is 3a over n, 4a over n, etc. The last one here is NA over n, which is a, and so that makes sense, right? Because you have n of these pieces, and the last right endpoint should be this point, right? If I follow this in. So if we use right endpoint to determine height of box, then the right endpoints are let's list them, shall we? The first one is a over n, and then 2a over n, 3a over n, and finally na. And for the cake box, this is the endpoint of the first box, a over n. 2 steps over is the endpoint of the second box. This is the endpoint of the third box. And this is the endpoint of the cake. Okay, I know each box is a over n in width, right? And I'm using the right endpoint to determine the height. So what is the height? What's the height of the first box? And how do I figure it out? In my labeling this in. The height is obtained by plugging into the formula here, plugging into the function, right? And what does the function tell me to do? Double me, right? Whatever I plug in, I double it, right? This is multiplication by 2. So I get 2a over n. Second box, what's the height of the second box? 4a over n. Third box, 6a over n. Keep doubling these things. What's the height of the cake box? Good. 2K. So now we're going to see the sigma notation step in here. So I can now give a formula, the area. Of cake box. The height, you guys have already told me, is 2K, A over N. And the width is A over N. So the area cake box is 2K A squared over N squared. So the area of all boxes. Well, we got our first box. And we got our second box. And we've got our cake box. And we've got our nth box, which is well, let's let it out. Yes, dynamic, yes. Okay, it's noxious. So it looks like it's actually as okay. 1 again, 2K A squared. That's it. So that certainly sigma notation. Notice how the formula works. K equals 1 is 2A squared over N squared. Bang. K equals 2, 4A squared over N squared. Bang. K equals 3. So let me get you a nice approximation. The total area of N boxes is given by the sum. This thing I've got here, 2K A squared. Now, A and N are changing at this point. So this is 2A squared over N squared times the sum. But we have an earlier formula about what this is. This is N plus 1 over 2. Y'all remember that formula. And so this is 2A squared over N squared times N plus 1 over 2. And I can cancel those two, I can cancel one N. I get A squared times looks like N plus 1 over.
Explain that again.
Okay, so are you with me up to here? Okay. And so all I did from here to here is I just replaced this summing notation. This, right? Okay with that? Just put this in instead of this. and then I cancel the 2. And I cancel 1 power, leaving me with an a squared and an n plus 1. Does that make sense? Notice when n equals 2, that was the first example I did when we broke it up into 2 boxes. I get 3/2 a squared, 3/2, and that's what I got. And then the next example I did was when n equals 4, I got 5/4 a squared. So this formula all works. Everybody okay with that? Everybody agreed that my 2-box approximation was sloppy, right? My 4-box approximation was better. If I had 1,000,000 boxes in here, it would look really good. How do you think we make it perfect? Our approximation seems to be better and better as it gets bigger and bigger, right? So what do you think we should do to make it exactly right? Doug? So what do we do to make it exactly right? Well, does everybody agree as it gets larger and larger and larger and larger, it seems to be better and better, right? Another way to write this, by the way, is a squared is 1 plus 1/n. Bring out 7 fractions. This goes to a squared as n goes to a. So even though our velocity was constant, my guess is the amount of distance that you cover if you're going at a velocity that's 2t would be a squared, a atoms. Any questions? Notice how my question about I'm going in an accelerating car that's accelerating at 2t miles per hour squared. Notice how I reduce this in a certain sense to a problem where I was in the areas of the curves. This is kind of one of the motivations for why we care about this. I'm going to give you a couple of definitions here. Well, actually, before I do this, before I stick it up there. So our question was, if we go from A to B, find the area. That's a motivating question. If we want this much more general than that, pass on. Idea is this. Break this up into, so I'm not going to make this really well defined. I'm going to kind of give this to you in broad strokes, and then we're going to look at it. Break the interval from A to B into small pieces. Two, use rectangles to approximate area. So maybe I do this. Because you know what? I don't know how to deal with curvy stuff, but this is the calculus idea. Calculus idea is see deal with limits. I can see if we can break this up into decimal pieces. I don't know the area under this curve. It's too curvy beyond my technology. So what can I do? I can break that up the interval up into little small pieces. And I can use rectangles under the curve to approximate. And would everybody agree that this approximation is at least ballpark there in the curve, right? By the way, if you put your eyeballs on it, do you think that this approximation, if I added up the area under all those black rectangles I got there, do you think my approximation is an overestimate or an underestimate of the actual area under the red curve? That's hard, right? I don't know. I'll buy that. Because here you're too big, you're really close. Here you're too little, you're a little bit too big, a little bit too big. Here it's probably a little bit too little, and you're too little on these right here. Right? So there's a little bit of give and take. But I mean, the fact that it's kind of hard to tell whether it's an overestimate or an underestimate here indicates to me that this might be a reasonable approximation. Do I agree with that? Okay, well, that's just an approximation. Here's the calculus I did. Use limiting process. Or exactly. What do I mean by that? I mean, look at what you've got here, and I haven't made what limiting process is besides yet. I'm going to do that, but here's the idea. Maybe this is 10 boxes, and I'm really not happy with it. So what do? I make 100 boxes. I make 1,000 boxes. I make 1,000,000 boxes. Everybody agree that if I divide that up into 1,000,000 pieces, it's probably going to be a really, really good approximation, right? How to make it perfect. Instead of just stopping at 1,000,000 or 1,000,000,000 or 1,000,000,000, keep the limit as n goes to infinity. Right? That's what we're going to do. But again, this needs to be made sense. Everybody understand what we're trying to do to measure the area of the curve? So putting the boxes in there, approximating and making better and better approximations. So I got to tell you some stuff. Definition. How many of you have heard the word partition before? Partition means to break something up. Like you might partition your garden, put this kind of plants here, this kind of plants here. You might, this room is partitioned, right? You four are at this table, you three are at that table, you're at that table. That's a partition, right? It's breaking stuff up into smaller pieces. This is what we're going to do with the interval. A partition numbers so and the little intervals x I minus 1 x I are subintervals. I'm not finished with the definition yet. I'm just kind of drawing a picture here. What I mean by the partition of the intervals is I just break it up into a smaller collection of intervals. So here's x1, x2, x3, x4, x5, xk minus one, xk, xn minus one. Here, subintervals, notice they're not all the same length, right? We've got this one, then we've got this one's a little skinnier still. This is a fairly long one, a little smaller. But a partition is just breaking this up. It's like taking a loaf of bread and slicing it into smaller pieces. Maybe not even with the same width, but. So when I say a partition of the interval, I just break it up. We say delta xi is xi minus xi minus one. This is just the length, say the width of I subject. So in other words, this width right here is delta x k. It's just how wide the interval is. We say the partition is regular if each delta xi, well, let me say that all delta xi are equal. So each delta x I delta x b minus n. This partition, the way I've drawn it, is not regular. Because the subintervals are a different length. This partition, I'm going to try to make it look regular anyway. This one's an attempt at regular because I tried to make it look like all the subintervals were the same. Any questions? So let me make a remark. If partition is regular, and the width of each is b minus a over n, then the left endpoints are given by, actually, this is right. A plus right endpoint kth interval is A plus A delta x. Now, let me try to explain this formula. Here's A, and here's B. All right. And each delta x, thickness of each of these is b minus a over n. Now, here's what this formula says. it says that the right endpoint, eighth interval, is given by this formula. Well, let's go through this. Let's just kind of check it, see if we can see the pattern. So the right endpoint, the first interval, this one, should be a plus one measure of delta x. There we go. Right there. The right endpoint of the second interval should be a plus two measures of delta x. There we go. The third interval, a plus three measures of delta x. And finally, I want to check this formula. Sure. What about the end? By the way, look at the picture. What should the endpoint of the nth interval be? It should be B. So this is a good check because let's see, we have A plus N delta X. Right? But delta X is B minus A over N. So this is A plus B minus A, which is B. So check. Play. What about the left? Anybody want to guess this one? It's very similar to one just off a little bit. What if I want the left endpoint? I want to go here, 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 and then stop at this. I'll give you, yeah, how about this? A plus blank delta X. That just pulls back, right? In case it's one, it's A plus zero. And then everything else is one behind. Questions? Okay, I'm going to do a problem kind of from scratch. This is kind of another sort of example I'm going to do here. And then I'm going to define formally something called the definite interval, and that'll be just a quiz time today. So, find area under first approximating the rectangles using right angle. And then so this should be exciting for you, right? Too much excitement for this early in the morning because this is something that you can't do up to this point. Right, and now we're going to kind of pioneer this. Let me draw you just kind of what this looks like. 1 minus x squared. This is friendly parabola here. Minus 1 and now, what I want to do is I want to break this up into, to make my life easier, Break up into, well, let's say, actually, we need a better word, here, partition into n equal space. By the way, if I break this up into n equal space boxes, what's the width of each box going to be? Here. Space done over. Space. Right here, I'm going to have a representative box. Say this is K. Okay. What's the width of each box that I have? Okay, question one, how wide is my interval? How wide is the whole shebang? There you go, it's 2. And we want it evenly divided into n pieces, right? So each delta x should be 2 over n. Actually, that's a minus b, 1 minus 1 over n. Like this way, but my b is 1 and my a is negative. Right, okay with that? Okay, I've got that going. All right. 2. Find height of a box. But first, I mean, to find the height of this king box here, what am I going to do? I'm going to plug my problem tells me to use the right endpoint. So if this is the K interval, I'm going to use the right endpoint to determine the height. And how am I going to determine height? What am I going to do with that? What is that picture? What am I doing in that picture? I take my right endpoint and do what with it? Right, so effectively what I've done is I've taken this point and plugged it into the function, 1 minus x squared, right? So I need to know what the right endpoint is to be able to plug it in. Somebody tell me what is the height? First I need right in. K box. And this. Well, let's take this apart. Each one of these is 2 over n wide. All the boxes, right? Because we've already figured that out. The right endpoint of the first box is -1 kicked over by 2 over n. Agreed? The right endpoint of the next box is -1 kicked over by 2 over n's. 3 2 over n's, 4 2 over n's. So I should be -1 kicked over by k 2 over n's. Everybody understand that? Is that okay? Sorry, I kind of missed what you said. So if I asked you, what's the right endpoint of first box? Notice this is -1. That ain't the right endpoint. So I'd have to kick it over -1 plus 2 over n. That's one length of it. If I got the next one, it would be -1 plus 2 lengths of 2 over n. and so forth and so on. But I want the K one, so I kicked it over by K widths to get it right in point of the K line. But okay.
Yeah, they'll get it in that. But the question is, so today, this is the big part.
This is the technique. This is the one I always find what the area of the K box is to develop your formula, right? But there are many ways that you can do this, but I think this way is efficient. So, yeah, and what the K box is depends on what the endpoints are, how wide the original, in this case, it's 2 units wide, and also where you start, which is negative here. So this is actually -1 plus 2K. Now plug this into when you plug that right endpoint in, it'll give you the height of your K box. So the height your height is going to be 1 minus you just got to fight the multiplier in that function. It'll clean up a little bit. Let me work this out. This is 1 minus, when I square this thing, 1 minus 4K over n plus 4K squared n squared. This. Everybody still with me? Okay, so 1 minus 1 is 0. This is going to be 4K over n minus 4K squared over n squared. This is the height. The width, because I split this up into even space bars, they're all, doesn't matter what K is, they're all 2 over n. So the area of K box is 2 over n times 4K over n minus 4K squared over n squared. Any questions on this? Okay, now what? Well, so my approximation add up all n boxes. So that's just summing this up. Sum area is approximately sum K 1 to n of 2 over n times 4K over n minus 4K squared over n squared. That's one box. This is me adding up boxes. Now I'm gonna massage this a bit, make it look over clean. Get a nice point. It's the sun. And everybody see what I did here? I wrote the sum up separately. So, for example, you could do this because if you had a, well, so really what you're doing, you're adding all this up, you distribute this out by six. Everybody come. And I can pull anything out of either of these sums like a constant as long as it's not changing, as long as it doesn't involve k. So for this first sum, I'm going to pull out 8 over n squared. And then the second one, I'm going to pull out 8 over n cubed. Maybe you don't know how to exactly implement this, steps in the next step. You should know these exist. Anybody remember what this is? From earlier today? Double gold star to get this. That's right there. Always remember that one does have a 6 in it. N plus 1, 2n plus 1, over 6. So here's what I get, my approximate formula. I get 8 over n squared, n plus 1 equal 2, minus 8 over n cubed, n plus 1, 2n plus 1 over 6. I'm going to clean this up just a tad. This is 4. Let's see, one end is canceled. This is 4 times n plus 1 over n. And this is minus 4/3. N plus 1 over 2n plus 1. Or times. So I can't, again, I can't split power. Well, there's a nice little compact formula here. By the way, this is 4 n plus 1, 1 plus 1 over n, minus 4/3. This is going to be 2n squared plus 3n plus 1 over n squared. So this is 4, 1 plus 1 over n, minus 4/3, 2 plus 3 over n plus 1 over. right? And I didn't do anything here. except manipulation. So my area is approximately uh, 4, 1 plus 1 over n minus 4 thirds times 2 plus 3 over n plus 1 over n. Everybody okay with it? Notice this works for any n. Right, so for example, if n equals 1, it would be 4 times 2, which is 8, minus 4 thirds times 5 plus 1 is 6, minus 4 thirds. So this would be like 8 minus 6. 8. So yeah, the approximation would be oh yeah, and of course if I had 1 box, the approximation has to be 0. And that's what I get. That's not a very good approximation. See, we're the curve equivalent in an area of 0. But for example, if n equals million, n is a million, this is very close to 4. Brings time. And this is very close to 2. Well, 4 thirds times 2, because these things can, as n goes to infinity. What do we get here? As n goes to infinity, what happens to 1 over n? 0. What happens to these animals? They go to 0. So I get 4 minus 4 thirds times 2. That's 12 thirds minus 8 thirds, which is 4 thirds. So in a certain sense, the exact area under that curve, that parabola, the exact 4 thirds. Okay. Question. Okay. I'm going to give 2 more definitions. I'll wrap up. Any questions? Okay, what did we do here? We did this parabola area. We put a bunch of boxes under here and use this to determine area. Approximate area that we get some kind of limit and so. Now we did this very regularly. We broke it up into even space intervals. We always use brain. We've actually got more freedom. Neat theoretically, you have more freedom. Practically, always want to do it like this. So I'm going to find something called Riemann sum, the definite definition. That f of x the function on say the interval from A to B. And if we choose xk star in subinterval xk minus 1 k, then f of x star delta xk is called Riemann sum. For this function on this interval. Notice this is a more general thing that we chose. With the parabola example, the other example done, each of these points were evenly spread out, and this xk star was just chosen at the right endpoint. This gives you a little bit. So let me draw you a picture for what Riemann sum looks like. Here's my A, and here's my B, here's my f of x. I can partition this any way that I want. This is x0, this is x n. Okay. Here's x1, here's x2, here's x3, here's x4, x5, xk minus 1, xk, xn minus. Now, this is the partition we have. Anything else I like with this, and the xk star, I often call this a test point. It is the point you use for determining height if you're going to make the right. So, and I can do this anywhere. I always forfeit the right endpoint, but anyway. So x1 star might be here, and you use it to determine the height of this thing. x2 star might be here, so it might be a right endpoint like we've done before, and x3 star might be here as well. So I might use the same point for the left endpoint of the next interval. But like I said, in general, you can put them anywhere. X4. Here's my test point here. I'll use this one to determine the height. X5 star here, determine the height. And in general, maybe xk star here. So this is a Riemann sum. That's it. It's just take the area of all these rectangles, axis, and this thing right here, for my picture here, the f of x is positive, so this is measuring a height. This is a width. So this whole chunk right here is an area. This means add up the areas. So all you're doing is adding up these green boxes. That's it. That's what a Riemann sum is. Yes. What is this? Just so I don't confuse this with one of these things, which are endpoints, right? That's why I put a little star there, because that's my test, right? So this is my population, and this is my little test. You gotta do something different. Okay. So let me give you now a definition here. Definition. And this is the final thing we do for this today. Let f of x be a function on the interval of negative. And the sum f of xi star delta xi be any Riemann sum. And what do I mean by any? That means any choice of partition and any choice. That's x1 star up to xx. So this could be any Riemann sum. You come up with any partition. We say f of x is integrable on AB if the limit of the Riemann sum star thing exists. We say it's integrable if this limit exists. The only limit is another one. So you take any partition, break this up into any partition you want here, and you do this Riemann sum. Now, what do I mean by this limit? This probably looks a little different. Remember, the delta xi's are the widths of these little subintervals, right? This limit, max delta xk goes to 0. That means even the fattest ones of these intervals are getting small. So they're all getting skinny, right? It's not really good to say as n goes to infinity, which is something that you're used to, because I could just make n go to infinity by letting all these be skinny and then leaving these alone. This is a technical thing that says, look, even the fattest of my intervals are getting small, so I'm getting closer and closer to the area of the curve. If no matter how you break this up, no matter how you pick these little these test points in here, if that limit always exists, and you always get the same answer for it, then we say that this function is integrable. Now, I've done some specific examples of this, where my partition was regular, that is, it was evenly spaced, and my test point was always the right endpoint. And remember how at the very end I took a limit and I got an answer? Well, if no matter how, if I instead use the left endpoint, if I use the midpoint, if I use something at random, if that limit always exists, and you always get the same answer, we say that this is the function is integrable. Now, in this case, we say the maximum delta xk 0 Riemann sum star and this is now I'll give you a couple of concluding remarks on this. You might be saying, hey Jim, isn't this an notation that you just used it before for anti-grid? Yes, now I've got numbers on it, but there's a connection. Now, let me point out a couple things. This looks horrible, right? But this is what we need to be on firm footing with respect to the mathematics. It is going to turn out. This looks like strong condition, right? I mean, no matter how I pick the partition, no matter how I pick my test points in there, I always have to have that limit exist, and it has to be the same thing. Actually, it's easier than a derivative as far as actually existing. And I'll be honest with you, if you had to do this crap we did today, every time you did these kind of problems, calculus would be useful or useless, right? Does everybody agree that these limits, it's awful, right? And how do I even do it with something that's not a polynomial? How do I do this with a trig function? How do I do this with an exponential? How do I do this with a log? If you had to do it by this limit every time, oh my goodness, forget it, right? We are going to have in the next couple of days the fundamental, it's called fundamental, it's the fundamental miracle of calculus. And it's what makes it so very, very powerful. Because even though this is a daunting looking limit, number one, like I said, it happens more often with functions than being differentiable. And number two, it turns out many problems, there's a much easier way to do it, right? Does everybody understand what I did with that parabola, when we did the boxes and all that? You all follow the steps that we did, right? But it's tedious. Nobody wants to do that every time. Say, find the area under a curve, and then you do three things to work. We're going to get something, a theorem that shows that this is actually really an easy problem for many functions. Okay, any questions? Okay, so do the homework in 4-1, and I've got you a little ways into 4-2, at least maybe a third or half way. So look at that, and we'll beat this up next time. Let's